Now let's remind the overall situation with basic concerns in continuity of functions and solve one of generic exercises that always happens when learning the topic. So basic thing, we are saying that some function is continuous in a point, like there, in x0, when it does have a limit there, and this limit is precisely a value of this function in this place. So we need to check both existence of limit and its value, and whether it is value of this function there. So as you may easily notice, it can be continuous only in points that belong to its domain. And here I listed the most often situations and basically the only ones we care about during our short class. Precisely, so-called jump discontinuity, so situation when our function is not continuous in some point, like there is a jump discontinuity, jump according to this large hole here. See that if it's our x0, of course the green curve is the graph of some function that we would like to be continuous. At this point we have actually value of our function, it's here included since it's the marked dot here. It has left-hand side limit, because going from the left actually tends precisely to this point, but unfortunately right-hand side limit going from the right actually would lead us precisely here, which is not only not the actual value we have, which is there, but also left and right hand side limits are different, meaning simply that there is no limit of this function at this point. And as you may easily notice, we cannot actually easily get rid of the problem, because wherever we would put the value here differently, the problem will remain. But there is no such problem in the very similar situation. There is so-called removable discontinuity. So again, some point is somehow shifted from the graph of our function to be the continuous line, but this time this jump is not a problem and not a concern. At this moment, of course, this function is discontinuous here, but see that left-hand side limit actually leads here and right-hand side limit as well. So not only both exist, but they equal the same number here. So the only problem is that our function takes value there. So if we move it, discontinuity will be removed and we will have very similar function, namely differing only by the value at one point, and we will get continuous function again. That's why it's called removable discontinuity, and this will be the situation we'll be dealing with the most, especially if we want to make some function continuous. We'll do one exercise soon. But there are of course also so-called essential discontinuities, also unremovable, happening in situations when in the point of concern at least one of the one-side limits does not exist. So not have wrong value, but does not exist at all. So here, of course, it does exist and is at the same point, but since we have here asymptote, left-hand side value actually escapes to plus infinity. So there is no left-hand side limit, so we cannot simply move one point to make it work again. So that's why essential. Of course, will happen also if both one-hand side limits doesn't exist. Not necessarily by diverging to plus minus infinity, but it will be our most common situation. Okay, so we can move on to solving a very typical exercise. We do have some function defined not as one generic formula, but by parts. So we have separation into some intervals or even points on which it takes different formula to find the value. So we have such function for negative numbers. At 0, it just takes some value, square root of b, whatever b is. And here we have some other function, some formula known for positive numbers. But there are two constants that we do not know, possibly a and b. And of course, depending on what values we will take as these a and b, this function might be or might not be continuous in all points of its domain. So let's think about this situation. According to basic properties you hopefully remember from class, but you have also listed in the appropriate PDF file attached here, every elementary function, its composition, their sums, and so on, so basically elementary functions overall, are continuous in their domains. So function f is for sure continuous here on this interval for all points. Similarly, this part on the interval of positive numbers, actually regardless of the value of a. So our only point of concern and the situation when the point can be in the wrong place, or maybe some appropriate one-side limit cannot exist, is point x equals 0. So if there can be some discontinuity, it would be here. So to make it continuous, we need to make sure there is a limit and that it has the same value as at this point. So first, of course, value at this point, so in 0, is just square root of b. This we already know from the definition. So now let's think about the one-side limits. So let's converge into 0 on arguments. From the left-hand side, reminder, that means from the left-hand side of f of x, of course. So, since from the left-hand side we are on the left from 0, and in the left from 0, this is formula of our function. So this is what we should put here inside. So let's find. We have x from the left, 0 from the left on axis, and we have for number e to x plus e to 1 over x. So since function e to x is elementary, so as we tend to 0, e to x tends to e to 0 being 1. So simply this part converges to number 1. Now if it comes to this part, it's like 1 over 0, but from the left. So we can have as large values as possible, but being on the left-hand side from 0, these are negative values below here. So it's like tends to e to minus infinity, or 1 over e to infinity being simply 0. So overall, our left-hand side limit is 4 minus 0, so it equals 4. So now we just need to check out similarly right-hand side limit. So in 0, converging from the right. But from the right, on positive numbers, of course, we have different formula from here. Let's put it inside. So we have sine of a squared times x over x. As you hopefully remember from the video about limits themselves, we actually know in 0 such limit, but we need to add here a squared. So argument in the sign and the denominator will tend to 0 at the same pace, but since it wasn't there, we need to multiply by it once more. See that I couldn't write it down if a is equal to 0, because then I would have division by 0 here, but it shouldn't be a problem, because if you would assume a equals 0, then it would be sine of 0 over x, so simply 0 for any x, so definitely not 4. There wouldn't be a limit, left and right hand side being equal in any case. So excluding 0, we have this one. So from the basic limits, this one tends to number 1. So overall limit, right-hand side limit of our function, is a squared. So if this function we would like to have actual limit in 0, left and right-hand side limits must be equal, or in other words, 4 must be a squared, leading to two situations, a equal 2 and a equal minus 2. And for this function to be continuous, function in point we think about, so 0, must be precisely the value of limit here. And we already found that limit exists when it's 4. Left and right hand side both are 4, so the limit is 4. So we can also add this up. Value of our function in 0 must be 4, and it's square root of b, leading to b equal 16, because square root of 16 is 4. But since we could have chosen A2 or -2, we have actually two different correct answers here. Either A2, B16, or A -2 and B16 as well. In these two cases, our function is continuous.